Hello and welcome to another video. In this video we're going to be doing the Mock Google Onsite, and hopefully don't get stuck anywhere. If we get stuck somewhere too long, maybe we'll just start reading an editorial or something, but we'll see what happens. Definitely not all these problems are super easy, so we're going to see. And the goal is just basically going to be 4 questions. Usually you get a hard in there, so try to do everything. Hard in 25, mediums in like 15 or something like that. Let's see how it goes. Okay, so we got 3. Okay, so there's a special keyboard with all keys in a single row. Given a string keyboard, 26. Your index finger's at 0 type of characters. You move your finger to the index of your desired character. Time taken to move your finger is the length of the distance. You want to type word, write a function that calculates how long. Okay. Okay, so this is the keyboard. The order of the keyboard, that can vary. And then, all right. Okay, so yeah, so all we have to do here is just like get a location for all of these, so we can just map each one of these letters to a location, and then from every letter we can just say like how much is it to go to the next one. So this would be at like index 3, this would be at index 2, so this would make 1 move. This would be 1 move as well. Oh yeah, and we have to start from 0. So yeah, I guess our finger starts at 0. Yeah, so this is 0. Or let's see. There are 26 characters. 0 to 25. Initially your finger's at 0. Okay. So to move from 0 to 2. Okay, so 0 to 2 is 2. Okay. So we start at 0, yeah, and then we basically just go from there. Okay, cool. So we got to make locations or something. Yeah. And then enumerate keyboard. Locations of v equals I. So now we have those, then we'll have a result, and we'll have a cur. And then for character and keyboard. Yeah, basically absolute value of the location of cur letter, which is going to be, or actually no, it's just gonna be the current location. So cur minus location of the letter we're going to. All right, and then cur equals the letter we're at now. All right, should be it, I think. Let's see. Oh, right, we have to do 0. Okay. Alright, let's see if we got it. Oh, we did not. Okay, let's see what we did wrong here. Let's print the locations first to make sure we got that correct. A is at 0, B is at 1, right? Yeah, that one's good. Okay. So for character, res plus equal cur plus locations char. So locations of C would be, so this would be 2, or minus, this would be 2. And then the new current is going to be 2. And then we go to this, so that yeah, it looks fine to me. I guess we can have some logs, so we can print cur. And res at the end. Alright, let's see what we get here. We can add some more if needed. Alright. Oh, this should not be. This should be word. That's probably our mistake. Okay. Looks good. So let's go for the submit. All right. Given the root of a binary tree, the level is 1, level of children, and so on. Return smallest level such that the sum of all the values at the level is maximal. Okay. So I guess we just, pretty simple again, we just do a level order traversal, and then we just like, yeah, so we just do a level order traversal, keep the sums, and then just return, if there's a tie, we're going to return the smallest one. Okay, so is there always a root? Yeah. Alright, so we'll just say the best level will be start at like 0, or we'll make it like -1 or whatever. and we're trying to maximize, so level total, we'll make it negative infinity. And we'll just do BFS. So dec of the root. All right, and then we say while we have a BFS, let's have a cur or total or whatever. 0 for this in range BFS. So you can do some Python, essentially just do a range comprehension over your current level. And if you add nodes, this doesn't change, this is like snapshotted. And then we can just get all those values. So node equals BFS pop left, total equals node val. If node left, add it to the BFS. If node right, add to the BFS. All right. So now that we have a total, so if total is greater than level total, then level total, and we need a level, right? So we'll have that as well. So I guess we can have like a counter or something. So level equals 1, and then at the end of the BFS, we'll up the level or something. So best level equals level, and then we just up the level from here. All right, return best level. Okay, seems easy so far. Unless we did it wrong. Float. Oh. All right. Okay, probably gonna get something difficult now. Well, we'll find out. So you're given an integer array R. From the same starting index, you can make jumps. So you have odd jumps, you have even jumps. Jumps are numbered. Okay. You may jump forward from any index I to j the following way. During odds, okay, so I guess we can write this down. So odd jumps and even jumps, since there's like a decent amount here. During odd jumps, jump to index j such that ri is less than j. Okay, so odd jumps, you jump to smallest index that is greater. Is this right? So wouldn't you always jump to the same one? Index j such that ri is less than or equal to rj, and rj is the smallest possible value. If there's multiple, you jump to the smallest. So wouldn't you jump to yourself, or you jump to the index that's like, yeah, basically yourself? I'm confused. Okay, let's maybe look at the example, because I am quite confused. Okay, so from 0. Okay, so I guess we can't jump to ourself. So that's a rule. We can't jump to ourself. Okay. So smallest index that is, now let's go back. That is less than or greater than or equal to our value. During even jumps, jump to smallest index that is less than or equal to our value. All right. Sometimes we have no legal jumps. Okay. Starting index is good. If starting from the end, at that index, we can reach the end. So, good index, we can reach the end. Okay. All right. Getting somewhere. Return the number of them. Okay. So let's see. So from 0. So yeah, we're going to jump to the smallest number that's greater than this, which is 12. Then we cannot jump anymore. Oh, do we only go right? Forward. Oh, okay, so we can only jump forward. Okay. Okay, that's important. So can only jump forward. All right. Yeah, so we go from 0 to 12, and then from 12, we have to go to a number that's smaller, but we can't. So I guess if we can't, we're just done. We can't like skip a jump or something. Okay, sure. From 1, so let's see without reading. Let's see if we get this correct. So we have to jump to the 14, and then from 14 we're stuck 2. Okay. From 2, we jump to 14 again, and then 14 we're stuck. Okay. From 14 we can jump to 15, and then we're done, I guess. So then we win. And then from 15 we're already at 15, so we win there. So these 2 is the ones we can do it. Okay, let's see if we get it. This one. So we have to jump to the bigger one, so 2 to 3. Then you would jump to 1. So yeah, 2 to 3 is odd, then even, then odd we jump to here, and then even we have to jump down, so we can't. Okay, I think. And then here, odd right away, so we can. Here, odd, so we go here, and then we can't. Okay, here, odd right away, so we go here, and then here we can't. So we can go here, here, and here. Seems like some DP thing, right? Like, okay, I guess. And then the last one. So here, we can't jump, or we can, no, we can't, because we have to jump to bigger, so we can't. Here, you would go here, and then here, so you can, so this one's valid. Here, you can go here and here, and valid. Here, you can't, and here you can. Okay, so these 3. All right, to do the 4th, okay. Okay, so kind of got the idea we can only jump right now. Obviously, we can't, like... So basically what we have to do is figure out a way to know, like, if some indices are valid or not. And the way to do that, like, obviously the last one, let's just take, like, this example. So maybe we can iterate through this backwards somehow. Yeah, we can't have n squared, so that's already out. Yeah. We can also figure out, actually... Okay, so what we can do is, like, some things that I'm thinking of is, like, from every index, we can figure out, like, if it's odd, where do we jump? If it's even, where do we jump? We can pre-process there. I think. Yeah, we should be able to do that. So, do we even need that? We'll find out. So for every index, figure out if jump is odd, where do we go? And then if jump is even, where do we go? And that's just like some next greater element or something, right? So we can just go like left to right and have like a stack or something, and anytime we get to a greater equal element, we can like pop off the stack. And the same thing backwards. So well, like once we have that, what can we do? Okay, well. So let's have another array of like, is it possible to make it? And we'll just go false, 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 false. Yeah, this is true. Okay. So from here, I wonder if we can do like a graph. I'm thinking yes. So let's just do this left and right thing, like odd and even. Yeah, so for every node, we have to know, like, are we there on an even or are we there on an odd? 4 is going to be true whenever. Or I wonder if we can just go backwards. Huh. Yeah, like, can we figure out, like, where we actually get to? So I guess if we start at a node, we're always there at an odd index. If we start a node, we're always there at an odd index, and then we just have to check like, okay, well from here, can we complete it? Yeah, maybe something like that. So basically we'd say like, this is the case for odd. Like if we start here, or if you jump to this node, on an odd index, you get this. For even index, you get this as well for now. Okay. And then we could say like, well, 1 is going to lead to 4. So I think if we process backwards, we could do it. 1 is going to lead to 4, so we'll be at 4 at an odd index. Sorry, even index. So that means 1 is going to be true. Okay. Now this one, and I think we're going to have to calculate it for both. So we can calculate it for both. So like here, we can also say, what if it's even? Then where will it lead? And if it's even, it can't go anywhere. So this will just be false. So then we're done. Then for this, we'll do the same thing. We'll calculate odd and even. So if it's odd, then we will go here. And then we'll be here on an even, which is false. So then this should be false. And what if we're here on an even? So if we're here on an even, then we'll be here on an odd. So this is true. Okay. Now here, if we're here at an odd, then where will we be on an even? So even is down, so we'll be here on an even. Even is here, so that's true. So this is true. And then if we're here on an even, oh, oops, wrong one. And then if we're here on an even, then we'll be wherever we're going on the odd, right? Like if this is even, yeah, maybe I screwed up the logic, but essentially like, or yeah, if we're here on an even, then we have to jump, we have to jump down, right? So we'd be here. And then we'd be here on an odd, which is false. So here on even is false. And then here, last one. So if we're here on an odd, then we're going to jump, we're going to jump here. So if we jump there, then that's going to be 3 on an even, which is right here. So we can't do it. And then if we're here on an even, we're going to jump here on an odd. And we can't do that either. So I think it's like this. And then we just return this odds array. I think that's it. That seems fine to me. Okay, so step 1, calculate this like next greater element and next smaller element. Step 2, compute these guys backwards. Seems good. Okay, let's give that a go. Okay, so for next greater element, maybe we'll do like null, and then if we have a next greater element, then we will, if we're like on an odd and we have no next greater element, we'll just mark that false and so on. Okay, so let's call this next greater, or graders or something. We'll mark them all none, times, we'll make a length of the array. Okay, so there, smaller. Okay. So essentially, we're going to traverse left to right and do this next greater guy. So we'll make a stack. And so what do we need to know? We need to know the index, right? Yeah, so. Okay. So while we have a stack, and how do I actually think just like this? So while we have a stack and the value is greater than or equal to stack -1, we'll have this be the value. We're going to pop and then mark the next greater index there. So basically stack -1 0 is going to equal, or this is going to be the index of that. So greater stack -1 0 will equal I and pop. And then we're going to append. So we're going to append the index and the value. All right, good there. Yeah. Now same thing backwards. So literally just traverse the other way. All right. I mean, we can do this, I guess. Okay. So this will be smaller. Yeah. I guess we could have done it in like a one pass, but who cares? Forget that. Yeah, so basically smaller is just... Actually, is this right? No, this is wrong. Yeah, so we actually do need to keep going the same way. I guess we are going to one pass here because, yeah, we're going the same way. It's always to the right. Call this like greater stack, and we'll call this like smaller stack. All right. So, greater stack. All right. Now we can just do smaller stack. Okay. And then we will definitely, this is pretty bad naming, I guess, but whatever. So this is smaller. Okay. So while smaller stack and this blah blah blah, so this is going to be smaller. Okay. So yeah, so while smaller stack and the value is smaller this time, so smaller is that, smaller stack, blah blah blah. All right, let's print those just so we can double check. All right, let's see. Okay, so in this example, 10 goes to is this right? No. Okay, so we don't want okay, so that's a tricky thing. We don't want the next grid, or we want the smallest that's to the right. Okay. Smallest to the right, that's bigger. All right, so I think this is actually harder than I thought. So I think we can do this with a min heap in a one pass. So we're just gonna collect elements in a min heap and then do it that way. Yeah, it seems correct. Probably do this one at a time as well, just to keep it simple. And then we have to do it backwards. Okay, so let's just get rid of all this. Go back to our original stack. Yeah, let's just go backwards. Okay. So we need a heap. Okay, so while heap, can we get... The other problem actually with the heap, now that I'm thinking about it, is like, we need... Maybe we have a stack this way, like a monotonic stack or something. And then we pop stuff. I mean, we can maintain like something sorted. Yeah, I guess we can maintain something sorted, and then we like... Yeah. So I think we have to maintain something sorted, and then figure out like what's the next greatest element with like a binary search actually. Which seems kind of not fun, but I think that's it seems like how we have to do it. So essentially maintain something sorted and then figure out like what's the next greater element using binary search. Now, how do we maintain something sorted? And is there an easier way of doing this? Like maybe we can like sort ahead of time. Okay, yeah, I think it's way easier actually. So I think what we can do is we can actually just sort the array and keep the indices, and then for every index, just look like what's the value to the right or the left. And that would be basically where we're jumping. But the other problem is... No, I don't know if that'll work. Because if we keep the value to the right and the left, like that value might not necessarily be to the right of the actual array. Yeah. So that would be problematic. Yeah, so maybe there's an easier way, but I'm just thinking, I guess we can have like a sorted list. That would work for sure. So if we have a sorted list, then we can figure out like how to, yeah, basically what's the index of the smallest element and what. So the sorted list can have like a number and an index, and then we can just do some binary search to find like the number that's greater than that guy, something like that. Yeah, basically like first element that's greater or something. Okay. Yeah, it's definitely getting complicated. I'm sure maybe there's an easier way, but I think because we have a lot of time, it's fine. Okay, so yeah, we're gonna go sorted list, and then we can use the same sorted list to get the item that's greater and smaller, honestly. Yeah. And then, yeah, okay. So I'm gonna look up sorted containers. Don't know this off the top of my head. And what we want is a sorted list. All right. So this is what we want. Let's just get rid of all this. Or at least, yeah, let's just get rid of it, to be honest. Put it up here, maybe. Okay. Yeah, so what was this? Sorted containers. All right. Maybe there's an easier way, but whatever, we'll go with this. All right, so no heap. All right, there we go. So what we have to do here is we have to basically say, like, if there is a sorted list, then we have to figure out the number that's greater. There might be like a built-in method already. Yeah. In here, I don't know for sure. Let's see, some methods. Index, bisect right. Let's see, find first value greater than a number sorted list. There might be like a built-in or bisect or something. Binary, okay. Yeah, I mean, we could obviously do a binary search. Whatever. All right, fine. Binary search. Okay, so yeah, and this will get inserted in login time, which is fine. Okay, so yeah, basically we can say like if the length of the sorted list is 0, just do nothing. And otherwise we can just do a binary search. Fine. Okay, so in the binary search we want to try every index, and we want, okay, so we'll just say like if length of the sorted list is 0 or there's nothing that's bigger, right? So if SL -1 at the value is greater than value, then we'll just continue because there's nothing bigger. Okay. And then, yeah. And so we'll just say like we want the smallest value that's bigger. So we'll say result equals sorted list at -1 at, or we need two things, right? So yeah, I guess we need two things. So we need like index is gonna be length of sorted list. Sure. And the result will be sorted list at -1. Okay, whatever. Yeah, and then we just binary search through this. Length sorted list +1. If sorted list at P1 is greater than value, then we'll replace. So sorted P, and yeah, actually I don't think we need a value. Yeah, I don't think we do. Okay, sure. And then we'll just try less. Yeah. Alright. Okay. Then we'll say greater, if there is one, which there has to be in this case. of I equals index. All right, let's see how this goes. And then we'll do the smaller as well. We'll just copy, like we're not going to focus on the cleanest code, I guess. For now, just have a solution. Let's get rid of all this. Yeah, definitely tougher. Okay, interesting. Oh, because we're never putting the item into the list. Okay, sure. So cell insert, I think. So we want to insert the index and the item. Other way. So actually, then in that case, this is going to be a 0. And this is going to be, what will the index be? Oh yeah, so index won't actually be P. It will be the index of this guy, right? So sorted list P 1, I think. Yeah. Okay, let's go for it. Let's see what we got. Okay, still get null. Why is that? Okay. Did we do the right insert for this? Sorted list. I think there's an insert, right? Sorted list. Update? No, add. Okay. Still interesting. Okay, let's print the sorted list. Wait, what? It's L. If sorted list. Oh, I see. Okay, so we don't want to continue. We still want to add. Okay. So I guess we can say if we'll do a pass. Else. This is like really bad, but fine. Just get something working first. All right. Okay, so now we got something. So, this is correct, I think. 3 goes to 3, actually. Is it correct? A number can't go to itself. Yeah, right? So 0, 1, 2, 3. A number can't go to itself, and this should be, yeah, so this is fine, but why is, oh no, actually this is fine, yeah. So this is 3, this is 3, yeah, this is good. Okay, perfect, so we got it. All right. Now I'll just go same thing other way, and we'll just redo this thing, and yeah. Obviously you can refactor and stuff, but don't want to make this too long. So, okay, so just bang. Okay, we're still going backwards. So now our sorted list is kind of the other way. So if sorted list is 0, or the small, so we're trying to get items that are smaller now. So sorted list 0, 1 is smaller than V, then we do a pass. Yeah, okay, yeah. And then if sorted list is smaller than V, then we do the same thing. Okay, and smaller. All right, and hopefully this works. Now we can print both. Or I guess we'll just print smaller. All right, let's take a look. Screwed up. How did we screw up? Are we not adding it again? No, we are. Oh, I need to print it. No, actually, it's fine. Let's print the sorted list. Just to make sure we're like doing things correctly. Okay, so we are adding the items. That's fine. What's the problem then? So 0 or if this, okay. Oh, we need, wait. If, no, the biggest number, right? If the biggest number is, so if we're trying to find greater, if the smallest is this correct actually? Yeah, so here we're trying to find greater elements. So that means the biggest, okay, this is if the biggest number is less than V, actually, this should be the opposite. If if the biggest number is less than v. So let's print greater again, because I think that was wrong. All right. No. Okay, so what am I doing? Okay, let's think about it. Okay, so let's say, yeah, so let's say our number, we actually did have it right before, so let's think why, I guess. So if the biggest number is smaller, then there's nothing greater, right? Like we're trying to find for odd, we're trying to find greater. Jump. Yeah, Ri is smaller. Okay, so length sorted is 0, or the value. Oh wait, where are we putting the value again? Okay, we're putting it at 0. Okay, so we just screwed up. Okay, so if the value, okay, let's try it again. Still null. Interesting. Oh, actually, I think I know why, right? So we're printing, yeah, so these prints aren't, this is the one we're printing. Okay, there we go. Okay, so 2, 3, 3, 4. Okay, we're good, I think. All right, so let's not print that. Okay, so smaller. So if we're trying to find smaller items, what do we need to compare? So if the smallest item is greater is what we need. Yeah. Smallest item is greater than v, then we pass. Okay, now let's pray. All right, is correct? 13, 12. Yeah, I think we're good. Okay. All right, I think we're good now. So now we have this greater and smaller. So yeah, now I guess the logic was, this is definitely a lot to this problem. Probably an easier way, but whatever. Okay, so yeah, I guess the next part is we basically have to make this evens and odds array, and then we have to mark everything as true and false. So let's do that. So I don't even know where to indent anymore. Okay, evens equals false times a, odds false. Okay, so now evens at the last index is true, because that's like our DP thing. Like the last number, no matter where you're at, is always doable. Okay, and now we have to go backwards and fill out the rest. So actually we're pretty close to an answer. Yeah. Okay, so just try and range a minus 2. Okay, so if we're on an odd jump, that's going to be, so if greater I, so this is the odd jump, and if, that means the next one will be even, so evens at greater I. If this is true, that means odds at I is true. Okay. Now the opposite. So if smaller I, so if smaller, that means we're on an even, so the next one has to be odd. So odds, smaller I, odds I equals true. Okay, this needs to be evens. All right, I think we're good. Now we just need to, so this part is actually pretty the easiest. So we just need to return the number of trues. So I guess, can we even do like odds? Does that work? Let's see here. Let's see area. I definitely don't like this like thing. Assembler. Let's see, I wrote that. Okay, yeah, I don't know why they don't have like a nice editor in here. It's kind of annoying. Okay. 2. All right, let's pray. Wrong answer. Interesting. Okay, let's try this test case. And let's print a bunch of stuff. So let's print greater. I guess I'll just make like enough string. Greater, smaller, and then evens and odds. Just to make sure all of it's correct and if our logic is flawed. Hopefully it's not. All right. Okay, so for greater, okay, interesting. This is 1, this is 4, 4, 4. That's correct. Smaller is this one. So 2, 2, correct. 1. Wait. Why is this 1? This can't be 1, right? It's an index. So this is incorrect. This is correct, but this should not be 1, right? This should be the index. So yeah, so this should be smaller. It should be 2, 2. Then here it should be 3. So how do we get 1? Yeah, I guess let's take a look at that smaller array, and that's a problem. Okay. Yeah, I also wish I could make this smaller, but I can't. Okay. So, yeah. Okay, so volume is this, or V, okay. If length is, if S00 is greater than V, let's go back to that example. Okay, so if S0, so it's going to be backwards. So in this case, it is not greater than V. Yeah, it's equal to V. So that's, we shouldn't pass, okay. So index will be the length of the sorted list minus 1. Is that right? No. Yeah, definitely not. But that shouldn't really matter. This can be like none, and I don't think it'll matter at all. Right, like if we do this, it'll be the same. I think. Oh, it did matter. Interesting. Okay. So, I guess what do we want to initialize it to then? So we want to initialize it to the biggest. No, the biggest element can't be smaller. So we'll initialize it to the smallest element, right? So we'll just go sorted list 0 and 1, and then here we want to go. Yeah, so sorted list, and then here we want just the biggest, so -1, 1. Let's see what we got here. 2, 2, 3. So now we have none, which is interesting. Should definitely not have none. Don't even know how that's possible. Yeah. Yeah, unless we're like not putting in the items or something. Yeah, let's print the sorted list here one more time. Okay, so we got 4, 4, 1, 3. Okay, so we got 1, 3, 4, 4. So we should initialize it to sorted list at index 0. Number 1. Yeah, that's correct. Okay, so maybe our logic is wrong or something, or yeah, I don't know. Let's see. So pivot. So if the sorted list at the pivot and item is smaller, then we want to go left. Actually, no. Oh, right. Smallest list, we want the biggest item, right? That's smaller or something? Let's see. Yeah. The largest possible value. Yeah, so this is the problem. So we actually want to reverse here. Alright. Definitely a lot of mistakes you can make in this one. Taking quite a while, but I think we're pretty close to finishing, so. Okay, so let's see now. Okay, so this should be 2. Okay, so these are incorrect now. Interesting. So is greater correct? 1. This is fine. Now this is not, I think. So 3, 3, 3. Yeah, this is not. So I guess let's think what would happen if we get to like this 3. So we have 1, 2, 1, 3, 1, 4. And we want the smallest index Oh, I see. So we want the smallest. Okay, okay. Huh. So if we want the smallest index, then we need to actually... I think what we need to do is in the sorted list, we need to check if the smallest index is already in there. And then if it is, we need to replace it. That's annoying. I think. Yeah. And we can just do that in a map, actually. That'd be easier. We can just have like a map of like index and then, or number and then index. Okay. Yeah, so let's just make another thing, map. So, map. Right. So, yeah, and then we're gonna, what do we need to do? We need to replace it, right? Yeah. So this needs to not be the index. So actually, sorry. What we need to say is, if this index exists, let's get the value and let's, or can we use a sorted set? Do they have sorted set in here? We could use that instead if they have it. Sorted set. Okay. Yeah, I mean, we could have a sorted set and then we can just like store the index in the map. Could do that as well. And then this has the same things like add, remove, index, and whatever. I guess. Okay. So let's modify this a little bit. So actually, you can't index a sorted set though, right? Yeah. I mean, we could use a sort. Actually, we can just use a sorted list and the map and then only store the number. Yeah, that would be fine. Okay. So let's just do that instead. So if sorted list -1 is less than v, will pass. Okay. And then index will be map of sorted list -1. All right, there we go. So if map of sorted list p0 or p is greater than v, then index will be, or sorry, if this is sorted list. So if sorted list p is greater, then index will be map of sorted list p, or m, I guess. All right, there we go. This is fine now. This should be fine. So here we need to go if the number is not in here already, if v not in sorted list, or yeah, is there like an in? I guess in. Let's see. In. Okay. So if v not in sorted list, then we'll add it in. And then we need to update the map regardless. So map v equals I. Okay. Okay, so essentially we just do the same thing for the other one. Yeah. Okay, so here, if the first item is greater, then there's nothing smaller. So that's that. Index equals the opposite, I guess. And then we'll remake the map. Definitely quite a mess. You can definitely make like a helper function for this. Okay. So yeah, I think if sorted list, or what was this? Sorted list p. Okay. Sorted list p is less than v, then index is map of sorted list p. All right. Okay. This is definitely getting annoying. Okay. Let's see. List and int and if length of s or sl0. Wait, what? is not supported. Sorted list is not supported. Are we adding? Oh, we're adding things in incorrectly. Okay. V. And same thing, if it's not in there. All right, let's double check. Here, what? Okay. Oh, we never did the map part. All right. A mess. Okay. Now, are we doing the right thing? Please, hopefully. So, okay, so greater. So this is 1, that's correct. 2, 3, 4. 4 for 4, okay. Smaller. 2, 2, and then it should be 3, right? God damn, what did I do wrong this time? Yeah, so this should be 3. So this one's still incorrect. So I guess we can debug now. And this is our sorted list. Yeah, so let's print it. Let's see. Okay, so yeah, so let's print here. I guess this is okay. Or no, let's print at the end, right? Yeah, let's print the sorted list in the map. And let's add this here and just print last. Okay, let's go. All right, so 4, 4 is correct. 1, 4, 1's a 3, okay. Okay, this is correct. So here, we should get a 3. Yeah. So how do we get a 4? I guess this is just like wrong logic, right? So let's take a look. So if length sorted list is 0, or sorted list is greater than v, it's not, okay. Map of, oh right, so this should not be the last, this should be the first. Oh, okay. 2, 2, 3. Okay, now we're good. Now we're outputting 5, should we? No idea. Okay, so we're outputting 5. Okay, now let's check this evens and odds and all this stuff in greater. Okay, so this should be true and true. That's fine. So our odds is also, what is it? It's only 1 true, so how do we even, where are we even doing that? Oh, right, we're probably doing it in the wrong spot. Okay. So this should be here. There we go. Okay. Run again. All right, so odds we're getting all true. Okay. Yeah, so let's just walk through this, I guess. So 4, it should just be true. 1, if you're on an even, we're looking for smaller. So yeah, I guess let's look at our logic. So if smaller I, it is not. Right, so this doesn't have a next greater or next smaller element, so that should just be false. That's correct. Okay, now if greater I, yeah, that should be true. So this is correct. Okay, so this is fine so far. Now this one, okay. So does this have a smaller? Yes. So if this is even, then the next one will be odd. So that's correct, right? Like we can go smaller and then upper. Yeah. If it's even. So if it's even, it should be true. If it's odd, then it should be true as well. That's correct. Okay. Okay, yeah, maybe I'm confused about like some reading or something here, because I don't know why this is false. Because like this is true. Like if this is true, this is true, this is true, this is true. So that's already 4. So let me reread. Maybe we misread. Okay, let me jump. Oh, so I see. So I think I screwed up the jumps, because the first jump. Wait, is the first jump? We can make it first since R2 is the smallest. Okay, this. So is the jump index? Let's see. The first jump. No, the first one is odd. So if 0, we can jump to here. Yeah, that's fine. That's what we did. Okay. So during odd number jumps, you can jump to any index to the right, such as the smallest possible value. If there's multiple, you jump to the smallest. Okay. Okay, so here you complete for sure. Here, you would jump here, and then you can't. Okay, so here you actually should get a no. I see. So what do we do wrong here? So here, so yeah, this should be true and true. This should be true and false. That's correct. Okay, here, so if we jump here on an odd, we're going to jump to 3, and that will be even, and that should be false. Yeah, that's correct. So this odd should be false. Okay, so that's what we're doing. Okay, so if it does have a greater, if evens greater I, so its greater here is 4. Wait, why is it 4? Oh, okay, this isn't correct. That's why, right? Yeah, so this is correct. No, the whole grader is incorrect. Now I'm looking at it. Yeah, the whole grader is incorrect, right? Because this is 1. No, actually, these two are correct, but these aren't, or this one is not. So in the case of a tie, there should be, you should pick the one to the right. So here it should go 1, 4, 3, 4. Okay, so the grader is incorrect. It's like that. So many mistakes. All right. So yeah, and then we're automatically getting the smallest index possible now. Yeah, I guess let's do a couple things here. So let's print this. Okay. And let's see what we did wrong. That's why this would be easier to make in a helper function, because we're just basically doing this work like many times. All right, so 4 is at index 4, 4, 1. Okay, this is good now. So here, yeah, so here we're getting this. So for this one, this is our sorted list, and we should get 3. And then the rest of it's fine. So why are we not? So I guess let's walk through that. So b equals right if length or, okay, that's fine. Okay, so we're saying it's 4 right now. Yeah. Oh, right. So this has to be greater or equal. And this has to be smaller or equal. Okay, now, there we go. Okay. Temp number 75. Let's console log or get rid of the P's and whatever. Yeah, definitely this, like, coding on this white thing is kind of bad. Hard to know, like, where your code is. All right, let's see. Submit. Pray again. Okay, thank God. Oh man, that was brutal. That last one was definitely pretty tough. Definitely haven't seen it before, as you could tell, hopefully. So yeah, this one took a while. I think the first two we just did so fast, so it's literally I just spent like all my time on this. But the nice thing is we kind of got the like the idea for it pretty quickly. Like I feel like most of it was just debugging. So yeah, I am curious if we look this up. What they use for a solution other than sorted list. Okay, interesting. Monotonic stack. Okay, and it's still in login. Tree map. So tree map is sorted list. Yeah, it looks like there's just a cleaner. I mean, well, if this is like 30 lines, I guess looking at lines. Yeah, I guess can I look at it again? Yeah, I mean, I don't know why this has print statements in there. I guess that's why it's so slow. But yeah, I mean, I copied code twice, so that can definitely be like smaller and whatever. But at least we got one of the solutions, so yeah, I think I'm pretty happy with that. Definitely could do better on this one. But for these hard ones, honestly, like, it's also like no hints and whatever. And I don't think it's super easy to come up with. I guess we can, yeah, I guess I'm just going to cut it here because the video is going to be too long. Let's see if we have a report yet. Yeah, definitely in the future going to try to, okay, so we do have a report. I mean, did okay, solved everything. Yeah, I think the main thing is maybe in the next ones I'll focus on code quality. I think I was just kind of a little burned out from getting so many things wrong. But yeah, hopefully that shows like a real debugging process, and like, not just doing these problems ahead of time and then having solutions that are always perfect. So hopefully that was helpful. Let me know what you think. Let me know what you think of these problems. Like, I do think it's a pretty fair, like, I think it's pretty good prep. As you can see, the problems are pretty tough. So yeah, thanks for watching.